Hello, in this lecture we'll study zeros and factors of polynomials. Specifically, we'll refresh the relationship between zeros of a polynomial and its factors. This is important to remember because factoring a polynomial was important in a previous lecture in solving polynomial inequalities and is something we'll continue to need to do. So it will become important to identify what the possible roots of a polynomial are and then perform polynomial long division to pull out its factors. Suppose f of x is a polynomial. Remember that if a is a real number, then a is a zero or root or x-intercept of the function, if and only if x minus a is a factor of f of x. The correspondence between roots and factors now prompts two questions. How can you find the zeros of a function? And if you have found a zero of a function, then if you factor it out, f of x can be written as x minus a times some new polynomial q of x. But what is that polynomial q of x? Finding the zeros of a polynomial is in general a difficult problem. However, if the function has integer coefficients, if all of the numbers multiplying the powers of x are integers, there is something called the rational zeros theorem that we can apply to try to find possible zeros. If, however, you already know a zero of the polynomial and you wish to factor it out and find the resulting quotient, we will do that using polynomial long division. So suppose the degree of a polynomial is 1 or 2. We can always quite easily find the zeros of that polynomial. Suppose you have a linear polynomial, degree 1, in slope-intercept form, f of x equals ax plus b. Setting this equal to 0 and solving for x quickly yields that x is negative b over a. There is one solution. So a degree 1 polynomial always has one root. Suppose f of x is a quadratic polynomial written in standard form ax squared plus bx plus c. You can factor, or you can use the quadratic formula. Now, when the degree of the polynomial is bigger than 2 and f isn't already given in its factored form, it is difficult to find its roots. There are some general techniques for degree 3 and degree 4 polynomials. These are formulas that are somewhat like the quadratic formula, but they are extremely unwieldy, and very few people ever actually use them. And in fact, for degree 5 and greater polynomials, no such formula can possibly exist to find the roots in general. This is a technical topic that we're not going to get into, but the point is, beyond degree 2, you should expect it to be difficult to find the roots of a polynomial. However, if the polynomial has integer coefficients, there is a way to find all possible rational roots of the function. The word rational here refers to being a ratio of integers. A rational number is one integer divided by another integer, which isn't 0. You can't divide by 0. So the rational zero theorem, also called the rational roots theorem, states the following. Suppose f of x is a polynomial given in its standard form, some number called a sub n times x to the n. Here n is the largest power of x, therefore the degree, and a sub n is therefore the leading coefficient, plus numbers times smaller powers of x, culminating in a constant term a sub 0 that is not multiplying any x. So remember, all of these coefficients have to be integers for the following theorem to apply. If p over q is a rational root of f of x, so p is an integer and q is a non-zero integer, then p is a factor of the constant term a naught, and q is a factor of the leading coefficient a n. So for example, suppose f of x is 3x cubed plus 7x squared minus 3x minus 2. Let's find all rational numbers that could possibly be zeros of the function. So the constant term is negative 2, and the leading coefficient is 3. Therefore, we are interested in factors of negative 2. This includes positive and negative numbers, and the integer factors of 2 are plus or minus 1 and plus or minus 2, and the factors of 3 are plus or minus 1 and plus or minus 3. So now what we do is we make all possible rational numbers or fractions we can, where we take a factor of the constant term, negative 2, divided by a factor of the leading coefficient, 3. So for the numerator, we could choose plus or minus 1 or plus or minus 2, and for the denominator, we could choose plus or minus 1 or plus or minus 3. So what is the possible list of rational numbers that might be zeros of this polynomial? Plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 3, plus or minus 2 over plus or minus 1, plus or minus 2 over plus or minus 3. Observe our numerators were choices for p, factors of negative 2, plus or minus 1, plus or minus 2. Our denominators, in contrast, were factors of the leading coefficient, plus or minus 1, plus or minus 3. So here we have a whole bunch of possibilities. Overall, this is plus or minus 1, plus or minus a third, plus or minus 2, plus or minus 2/3. That's 8 possible different rational numbers. The point is not that these are all roots of the function. They can't possibly be. However, any rational number that is a root must belong to this list, and this list only has 8 terms in it. So there are only 8 rational numbers that can possibly be zeros of the function. Out of these 8 numbers, they are not all going to be roots. Which ones are? All we have to do is actually plug them into the function and determine are any of these roots of the function f of x. So we plug in 1, and if you compute f of 1, you'll end up with 5, so 1 is not a root. Negative 1 is not a root. 2 is not a root. Negative 2 is not a root. Observe we're not going strictly in the order of our list. We're actually going in an order of what's the easiest to compute first. Now let's plug in a third, not a root. Negative a third, also not a root. F of 2/3, however, if you plug that in, you will see that f of 2/3 is 0. So we have found that x equals 2/3 is a root of the polynomial. Negative 2/3, however, is not. So 2/3 must be the only rational number that is a root of this function. Suppose f of x and g of x are polynomials. If we're asked to divide one polynomial by another, the goal is to produce 2 other polynomials, q and r, for a quotient and remainder respectively, so that f of x is g of x times q of x plus r of x. Observe that if we were to divide by g of x, we would have q of x plus a ratio r of x over g of x. So dividing this expression by g would say f over g equals q plus r over g. And we need to find what q and r are. So q is called the quotient, r is called the remainder. And if you've heard these terms before, it's extremely similar to classical long division of integers. The remainder is either going to be 0 or a polynomial whose degree is strictly smaller than the polynomial we divided by, g of x. So the setup and steps for long division are quite similar to those for long division of integers. For example, let's divide 6x cubed plus 8x squared minus 2x minus 4 by 2x squared minus 1. We want to identify the quotient and the remainder. Now, we're dividing this by that. So this is going to be our denominator, 2x squared minus 1. It has degree 2. We conclude the remainder must have smaller degree. It is either of degree 1 or 0. So if you conclude polynomial long division and your remainder does not have smaller degree than what you were dividing by, something went wrong along the way. So at the end of the problem, we already know our remainder will have degree either 1 or 0. So first we set up long division. So we make our classic sort of division sign. Here's what we are dividing, and that's what we're dividing by. And what you do is you proceed by largest powers. So the largest power here is 6x cubed. The largest power here is 2x squared. Perform that division. 6x cubed divided by 2x squared. 6 over 2 gives us 3, and x cubed over x squared gives us x. So 3x must be part of the quotient. We're going to align it, 3x, which has power 1 here, it's a linear term. We're going to align it with the linear term of what we started off with. Now, take the thing you were dividing by, multiply it by what you just identified, and line it up underneath. So we end up with 3x times 2x squared. We already know that gives us 6x cubed. It's how we determined to put a 3x there. But now we have this minus 1. 3x times minus 1 is minus 3x. I'm going to align it with my x term here. We're going to keep a 0 here just to make sure we didn't forget that there's a squared term, but we didn't generate it because observe that our denominator, 2x squared minus 1, doesn't have an x term in it. So when I multiplied here, I didn't get a squared term. That's fine. We just put a 0 here to remind ourselves that it should be there. Now we're going to subtract this entire quantity from what we started with. So 6x cubed minus 6x cubed is going to be 0. If you're doing this process correctly, you're always going to be canceling out the largest power that remains. Because you started with this divided by that to get this term here, meaning this term here times that one should exactly cancel out that largest power. So if you're doing this correctly, every step cancels out the largest power that there is. So 6x cubed minus 6x cubed is going to be 0. 8x squared minus 0 is going to be 8x squared. Negative 2x minus 3x, and here is by far the most common error we see students make is problems with distributing minus signs. But negative 2 minus negative 3x is x. And don't forget to carry down this constant term, because there was no constant term here to subtract, consider it to be a 0. So this minus 0 is minus 4. So we started with a degree 3 polynomial. Once we identified a single term from our quotient, we now have a degree 2 polynomial. All we have to do is repeat the same steps. What's 8x squared, the largest power here, divided by 2x squared, the largest power here? Well, the x squareds cancel completely, and you simply get 4. So 4 is part of the quotient. It goes with the constant term. Put it there. Now I'm going to multiply that 4 by the 2x squared minus 1. That gives us an 8x squared minus 4. We have a 0 here for the linear term, don't forget. Now we subtract that entire quantity. The largest power cancels out. That's great. That's always going to happen at every stage. And all we have left is this x. Observe, 8x squared minus 8x squared cancels, but negative 4 minus negative 4 also cancels. So all we have left is x. Now the process stops. If you attempted to do x divided by 2x squared to keep going, well, you could cancel this x here, but you would still have an x left in the denominator. So you wouldn't have a polynomial, and we're only doing polynomial long division. It is technically possible to continue this dividing process, but you end up generating non-polynomial functions. Leave that aside for another time. So as soon as you have something here whose degree is smaller than what you are trying to divide by, you can't keep going. So the quotient is what we have produced up top, 3x plus 4. And the remainder is what we have left when we can no longer do the division, which in this case was just an x. And in fact, you can check that if you take 6x cubed plus 8x squared minus 2x minus 4, that is exactly equal to what we divided by, 2x squared minus 1, times the quotient we found, 3x plus 4, plus a remainder of x. Observe, 2x squared times 3x gives us exactly the 6x cubed. How can I possibly get x squared terms? 2x squared times 4 gives us 8x squared. How can I possibly get linear terms? Negative 3x plus the remainder here gives me negative 2x, and the only constant I can get is negative 1 times 4. So indeed, we have identified the polynomial we started with is in fact equal to what we divided by times the quotient we found plus the remainder we found. This is how polynomial long division works. So let's do another one. Find the quotient and remainder for 2x cubed plus 20x squared plus 8x minus 10 divided by x plus 1, and we'll move through this example a little faster. So we set up our division sign. We put the 2x cubed plus 20x squared plus 8x minus 10 inside it. We're going to divide by x plus 1, and now we play the game, divide largest remaining power by largest power, and cancel things out as we go. So 2x cubed divided by x is just 2x squared. So that's part of the quotient. Put it there with the squared term. Now we multiply the x plus 1 by the term we just got, which gives us 2x cubed plus 2x squared. We're going to subtract that entire quantity. The x cubed terms will cancel, the largest term always should, giving us 18x squared, and we carry down the other terms as we go, 8x minus 10. Now we continue. Let's divide 18x squared by x. To get 18x, that's part of our quotient. Put it with our linear term. Multiply this by the x plus 1 that we're dividing by to get 18x squared plus 18x. So we align those as so. And now we're going to subtract that entire quantity. The x squared term cancels. Hooray. Negative 10x minus 10. Okay, can we divide these? Sure, we've got degree 1 and degree 1, that's fine. Divide negative 10x divided by x, the x's cancel, we just get minus 10, so that goes in the quotient. Now we multiply that to get negative 10x minus 10, and observe that when we subtract this entire quantity, everything cancels and we get a 0. So the quotient is what we found up top, 2x squared plus 18x minus 10, and the remainder is 0. You can, in fact, verify that x plus 1 times this right here, the quotient we found, plus no remainder at all gives the original polynomial, this cubic here. Okay, how can we get cubic terms? 2x squared times x gives us 2x cubed. How can we get squared terms? 2x squared times 1, but also 18x times x. Altogether, 2x squared plus 18x squared gives us 20x squared, etc. You can check that the product works out. So the remainder at the end of this is 0. So we're going to conclude with an example where we put all of these things together. Let's find all of the real zeros of the cubic polynomial f of x equals 2x cubed plus 11x squared plus 8x minus 1. Because we have something larger than degree 2, we're going to start with the rational roots theorem. That only applies when all of the coefficients are integers. The coefficients are 2, 11, 8, and negative 1, all of which are integers. Therefore, the rational roots theorem applies and says the only possible rational roots are factors of 1 divided by factors of 2. I say factors of 1 instead of minus 1 because factoring includes positive and negative together at once. So the only possible things in our numerator are plus or minus 1, and the only possible things in our denominator are the factors of 2, plus or minus 1 and plus or minus 2. So that generates a pretty short list, plus or minus 1 over 1 or plus or minus 1 over 2. So there's only 4 rational numbers that could possibly be roots of this function. So let's actually test them by plugging them into the function. F of 1 is 20, so it is not a root. F of negative 1, however, is 0. We have found a root. 1/2 and minus 1/2 are not roots, as it turns out. So the only rational root is x equals negative 1. If x equals negative 1 is a root of the polynomial, then x plus 1 can be factored out. In other words, factored out with 0 remainder for some polynomial q of x. So let's find what q of x is by doing the polynomial long division. So we set it up, and then we start taking ratios of largest power terms. 2x cubed over x is 2x squared. We multiply that across here and take the difference. The largest term cancels out, leaving behind this degree 2. 9x squared over x is 9x. We multiply that, subtract it. The largest term cancels out. Now we have negative x minus 1. Negative x, the largest power of x down at the bottom there, divided by x, the largest x that appears in our denominator, the thing we're dividing by, is minus 1. Multiplying x plus 1 by negative 1 gives us negative x minus 1. When we take this difference, everything cancels out. Lo and behold, we have 0 remainder. So what we found is that this quotient is exactly 2x squared plus 9x minus 1. Therefore, the polynomial we started with, once we factor out x plus 1, the resulting quotient is 2x squared plus 9x minus 1, and there is no remainder to worry about. If you have a root of the function and you do this long division, you should get 0 remainder. If you don't, something went wrong. Students often ask also, what about synthetic division? Synthetic division is a particular technique for doing long division of polynomials when you have a very particular setup. Because it doesn't always apply, we generally don't like to cover it. But if you know how to do it and can do it properly, most instructors will let you do it. We don't cover it in this course because it is not always going to be an option for all scenarios of polynomial long division. So far, we know that x equals minus 1 is a root of this polynomial we started with, and once we factor out the corresponding factor of x plus 1, in other words, x minus 1, the quotient was 2x squared plus 9x minus 1. So any other roots of the function must come from that factor, 2x squared plus 9x minus 1. So can we set that equal to 0 and solve for x? Well, the good news is that this is a degree 2 polynomial, and you can always find roots of these from the quadratic formula. So throwing the quadratic formula at this resulting degree 2 polynomial gives us x, possible root, could be negative 9 plus or minus the square root of 9 squared minus 4 times 2 times negative 1 over 2 times 2. This simplifies to negative 9 plus or minus root 89 over 4. So here are 3 zeros of the polynomial. X equals negative 1, x equals negative 9 plus root 89 over 4, and x equals negative 9 minus root 89 over 4. Now something to point out is that x equals minus 1 gave us a factor of x plus 1. These also give us factors. If you desired, you could now factor this bit here as x minus negative 9 plus root 89 over 4 times x minus negative 9 minus root 89 over 4, corresponding to the fact that we found these as roots, these must be factors. So this would be the polynomial in its fully factored form. Another thing to point out is when we applied the rational roots theorem, we found a list of rational numbers that could possibly be roots, and the only rational root was x equals -1. These are roots, but they are not rational numbers. They are not possible to write as a ratio of one integer divided by another. So they are real numbers that are roots, but they are not rational roots. And finally, the last thing to point out here is we found 3 real numbers that are roots of this cubic polynomial. The number of real roots cannot be larger than the degree. Because every root you find corresponds to a factor of x minus something, each of these factors is of degree 1. If you multiply them all together, the corresponding degree would be how many roots you found. So the most number of roots you can possibly find is the degree of the polynomial. And I say the most, not exactly equal, because some quadratics do not have real roots. If the quadratic formula gave you a negative number under this radical, you would say there are no real roots and that quadratic is irreducible. It cannot be factored. If you're working in the complex numbers, then all polynomials can be factored into exactly as many linear terms as its degree. But if you're not using complex numbers, you would say that the number of real roots cannot be bigger than the degree. So having started with the degree 3 polynomial, we could only find at most 3 real roots. Since we have found 3 real roots, we must be done.